Apex rocketry entry for 2020 Latin American Space Challenge is the Armação project. The Armação has the main objective to design a solid-propelled rocket for the nominal apogee of 1 kilometer and establish a knowledge base and design reference for team future projects. The financial resources needed to build all rockets sum to 4,968 reais, shared between the team's project areas. For each area, the cost of safety equipment needed for manufacturing was also taken into account. Among the areas, electronics account for 49% of our budget. The following graphics detail the biggest expenses per area in aerostructures, recovery module, 3D connectors, and fuselage. In electronics, payload, avionics, and igniter, and propulsion, engine machining, propellant, and engine peripherals. In the superface section from the motor, here we've got the combustion chamber, the nozzle, the bulkhead, and the upper support. The bulkhead is the tube closing piece, and its seal is reinforced by the support element. The upper component serves as an extra sealing with rings between the two parts. As the motor parts required high precision, they were manufactured by one of our sponsors, Avionics. In order to know the chamber's strength, a structural simulation was made. The results obtained were a volumetric stress of 49 megapascal in the chamber center, resulting in an average safety factor of 2.5 for maximum motor load analysis and considering internal pressure as 1.5 times the nominal. The maximum thrust is 976 newtons, with an average thrust of 950 newtons and total impulse of 2,942 newtons per second, thus a Class L motor. The maximum pressure found was 2.45 megapascal. The rocket has 4 grains, all with composition of 65% potassium nitrate and 35% monohydrate dextrose. This percentage is corrected by the factor 1.1 in mass due to hydration. The external face is inhibited with a cotton cloth and epoxy resin. The combustion chamber also has a thermal insulation element based on craft paper. Parametric study was carried out using open rocket and was concluded that for 1 kilometer apogee, each grain has 110 mm length, 66 mm of external diameter, and 18 mm for core diameter, with a boilerplate payload of 4 kilos. A team is at the beginning of the test schedule, with results just for half-cargo motor. The results for the first test were satisfactory, occurring without anomalies and demonstrating the combustion chamber's structural integrity. In this test, we used craft paper as inhibitor. A nominal static margin of 1.6 calibers was achieved with the help of 3 fins and 3 canards. The canards were chosen to reduce the static margin variation and improve the damping ratio, while combined with the main fins, maintaining a safe minimal static margin. The majority of its mass is concentrated in the propulsion module. The rocket's stability and flight mechanics were evaluated for different launch angles and wind velocities. The critical environmental conditions were obtained for both rocket configuration, maintaining an acceptable horizontal range and safe liftoff static margin of around 1.6 calibers. Statistical Monte Carlo trajectory simulations allow the team to know the spread of the landing locations and establish a safe perimeter around the launch site. Safety analyses were performed for different aerodynamical conditions using ANSYS fluent. The different proposed fin set configurations were compared to determine a minimal drag fin design. The rocket's drag coefficient and the static margin could also be determined, validating open rocket simulations. The rocket's fuselage was laminated with fiberglass and epoxy, as well as the fin set, but tail and nose cone. Several simulations were necessary to evaluate the parts under maximal aerodynamical and pressure loading and maximal thermal loading due to the motor. Aeroelasticity simulations were also carried out to foresee further critical conditions. The recovery mechanism is mechanically actuated, with the structure is reinforced with balsa wood and PVC structure built to absorb and reduce the stress caused by the parachute lateral cut. The altitude data is managed by the altimeter. When the target value of 400 meters of 1 kilometer mission is captured, the initialization of the recovering system starts. A direct current electrical signal is sent to the linear actuator, releasing the airlock. The parachute hatch is then ejected due to elastic bands that push the parachute upward. This system is actually symmetrical and redundant. It is built using 2 identical systems containing an altimeter, battery, and an actuator that not communicate with each other in any way. In addition to that, the system is projected to work even if one of the airlocks is not released for some reason. The Avionics and Payload subsystems are located on the rocket's force section. Its main objective is logging and transmitting in-flight real-time data that will later be processed and analyzed. The Avionics subsystem records the most important and necessary data. Used to validate our efforts, it contains an ESP32 microcontroller, GPS, power lines, and lithium batteries on the top side. The batteries have a voltage monitor and are protected from overcurrent. At the bottom side, we have the MPU sensor capable of 3-axis gyroscope and accelerometer measurements, the BME for barometric pressure, temperature, and humidity measurement. We also have the 1 watt low-high for transmitting vital data, and the micro SD for data logging, as well as a buzzer for sound feedback. The other side of the avionics board holds the MPU, a 3-axis gyroscope and accelerometer, the BME sensor used for measuring barometric pressure, temperature, and humidity, the 1 watt low-high for transmitting real-time vital data, and the microSD for data logging, as well as a buzzer for sound feedback. Thank you for your time.